In this class, we will introduce how to calculate and determine the main parameters of the caster. The main design parameters of the continuous casting machine include the size and shape of the section of the billet, the casting speed of the billet, the metallurgical length, the radius of curvature of the caster, the number of the strands, the production capacity of the continuous caster, etc. The section shape and size of the billet are mainly determined by the requirements of the rolling mill. At the same time, the actual section size which could be cast and casting quality of the billet should be considered together. Section shape and size have the direct impact on the productivity of continuous caster. Generally speaking, the same casting speed, the greater the section, the higher the production capacity of continuous caster. When the thickness is the same, the slab productivity is higher than billets. The section range of the billet produced by the current continuous caster is billet 50 times 50 to 450 times 450 mm. Slab maximum is 420 times 3100 mm. Round billet 540 to 450 mm. Beam blank 120 times 240 mm oval. 450 times 100 mm holy blue molding. 356 times 775 times 100 mm S shape. What is casting speed? The casting speed is an important design parameter to determine the production capacity of the continuous caster. Appropriate casting speed can not only exceed the production capacity of the continuous caster, but also improve the surface quality of the billet. There are many factors that affect the casting speed, such as the size and shape of the section of the casting billet, the steel grade, the casting temperature, the length of the caster, the resistance of the casting billet, and the solidification thickness of the casting billet after the mold outlet. The maximum casting speed must ensure that the casting billet have enough thickness after casting billet out of the mold. According to the law of solidification, the thickness of billet shell, dirt, equal to it times square root tau. The setting time of the billet shell, tau equal to h squared divided by 4 times 8 squared. The theoretical calculation formula of the casting speed is V equal to Lm divided by tau equal to Lm times 8 squared divided by dirt squared. Unit is millimeter per minute. In the formula, Lm is effective contact length of the mold, it solidification coefficient. To small section cast billet, it is 28 to 31. To large section billet, it is 24 to 26. Metallurgical length is the calculated length of liquid phase according to the maximum casting speed of continuous caster, which is related to the thickness casting speed and cooling strength of the billet. Metallurgical length is related to the determination of the caster and the basic radius of the curvature of the continuous cluster. The definition of the metallurgical length is also called liquid core length, is the distance traveled by the molten steel from the molding level to the complete solidification. Normally, there are two ways to calculate metallurgical length. One is with the liquid core, the other is without the liquid core. Normally, metallurgical length is greater than or equal to liquid core length. According to the law of the solidification, when the billet is completely solidified, the relationship between billet thickness and times is h equal to 2 times 8 times square root tau, and tau equal to h squared divided by 4 times 8. Assuming casting speed is v and liquid core length is L, then L equal to v times tau equal to open bracket h squared divided by 4 times 8 squared close bracket times v. From the above equation, we know the larger h and v are, the longer L is, and the longer the casting machine is. In the design, consideration should be given to the maximum thickness of the billet that can be cut by the cutter and maximum speed that can be reached. The arc radius of the cutter refers to the outer arc radius of the billet when it is bent. It is an important dimension parameter of the cutter. It affects the total height of the cutter and equipment weight, also affecting the quality of casting billet. The smaller the arc radius of the cutter is, the smaller the size of cutter will be. However, the arc radius too small will cause cracks due to the excessive elongation during straightening. That is, the arc radius of the cutter is limited by the elongation of the slab during straightening. There are two ways of straightening: solid phase straightening and liquid phase straightening. Let us see how the arc radius is determined when solid phase straightening. When a cutter casting special steel, the general requirement of the billet into the straightener should be completely solidified. This is called solid straightening. The cutter radius could be determined by the formula R greater than or equal to 0.5 h divided by epsilon 1. Epsilon 1 is the allowable strain or elongation. Epsilon 1 equal to 1.5% to 2%. So, the radius of the casting machine is determined only when the billet is completely solidified before straightening. Then, we should check whether the billet is completely solidified from steel level of the mold to the straightening roller. Calculating the arc length LC at this time. The formula is LC equal to pi divided by 2 times open bracket R minus D divided by 2 close bracket plus Lm divided by 2. LC is arc length from the steel level of the mold to the straightening roller. Lm, effective contact length of the mold. R, arc radius of cutter. D, thickness of the billet. We calculate the liquid core length. L equal to V times tau equal to open bracket h squared divided by 4, 8 squared, close bracket, times V. If L greater than LC, it means the billet is not fully solidified. We need to use L as the arc length for assuming complete solidification. Calculate R reversely. The formula is R smaller than or equal to 2 divided by pi, open bracket, d square divided by 4, it square times v, minus Lm divided by 2, close bracket, plus d divided by 2. How to determine the arc radius when the liquid phase straightening? The allowable elongation epsilon 2 equal to 0.15% to 0.2%. In two-phase region of the inner arc liquid cell during the liquid phase straightening, it's much lower than epsilon 1 equal to 1.5% to 2%, like during the solid phase straightening. Therefore, the radius of cluster will still have very large when the liquid phase straightening is at 1 point. And the purpose of reducing the radius and increasing casting speed cannot be achieved. Therefore, it is impossible to adapt 1 point straightening under the condition of high casting speed. So, the liquid phase multi-point straightening is proposed. The formula of the liquid phase multi-point straightening is as the slide. Here, Rk plus 1 is the calculated radius of the cluster in K of K plus 1 straightening. Delta K plus 1 is the thickness of the billet shell in K plus 1 straightening. D is the thickness of the billet. Epsilon 2 is the allowable elongation of the liquid phase straightening. Firstly, how to reasonably match our continuous cluster and steelmaking furnace, and how to determine the number of cluster size. First, strictly controlling the required composition, temperature, and quality of the molten steel, and maintaining stability. To this, it must be equipped with the corresponding external molten steel treatment equipment. Second, the smelting cycle of the steelmaking furnace should be coordinated with the casting cycle time of the continuous cluster. Third, the hourly production capacity of continuous cluster should be balanced with hourly output of steel furnace. Fourth, ladle, tandies, and submerged nozzle should be long life and quick replacement. High quality refractory material should be used. Quick replacement measures should be taken. Fifth, continuous casting subsequent process such as billet discharge, slab sizing, and transportation capacity should meet the requirement of multi-furnace continuous casting. Secondly, we should know the continuous casting billet yield. The yield of continuous casting billet refers to the output of qualified billet within a specified period of time, generally in months or quarters or years. The calculation formula is continuous casting billet yield equal to the total amount of production billet minus the amount of waste after inspection minus the amount of waste after rolling or retained by users. The continuous casting billet must be produced in accordance with standards or in accordance with the standards and technical agreements stipulated in the supply contract. Third, we should know the operation rate of continuous caster. The operation rate of the continuous caster refers to the percentage of the actual operation time of the caster in the total cylinder time, generally calculated by month, quarter, and year. It reflects the operation and production capacity of the continuous caster. The calculation formula is on the slide. Generally, billet culture is 60% to 80%. Bloom culture is 60% to 85%. Slab culture is 70% to 85%. The operation rate of special steel continuous culture can be lower. Next, we should know the yield of continuous cutting billet. The yield of continuous cutting billets refers to the percentage of qualified production of billet in the total amount of the molten steel. It accurately reflects the consumption of the continuous cutting production and the collection of the molten steel. The calculation formula is on the slide. Generally, the yield rate of continuous cutting billet is calculated annually. The yield of billet is about 96% for single cutting, 97% for the 2 continuous cutting, and 98% for more than 3 continuous cutting. That's all for today. See you next time.